Okay, this is the final in the session about hill slope geomorphology and modelling. And now we're going to talk about landscape evolution models. And landscape evolution models essentially look at long-term development of hill slopes. And this can be important, particularly where you have landscapes that might be impacting particularly sensitive areas, such as the Great Barrier Reef, for example, or Kakadu National Park. And where you may have contaminants such as radioactive material that might be long-lived. So for example, if you're storing radioactive waste and you're putting it at the bottom of a mountain, a hill, an artificial hill, what's going to happen to that hill in 10,000 years' time when that material is still radioactive? Okay. Even though we're not going to be around to worry about it, someone else is going to have to worry about it if we haven't destroyed the planet by then. Right, so there's a bunch of models that we can use to simulate landscape evolution. And often they're based on simple equations which can describe sediment transport in terms of very simple components. One's a fluvial component, which is related to the water flow. So you would essentially simulate the water flow in that landscape and then get the fluvial discharge, which then you can have a fluvial component to your sediment transport. And then the other one is a rain splash component or a soil creek component or some sort of diffusive sediment transport, which is maybe impacted by wind, erosion and other things which tend to smooth out the landscape. So the fluvial transport incises the landscape and cuts little gullies and channels, whereas the diffusive transport term smooths it out, and it's like shaking the plate if you had a pile of sand and you shake the plate, diffusive sediment transport would be a bit like that, spreading it out and making it smoother. So we can actually get the total sediment transport as being a combination of both the fluvial transport term and the diffusive transport term. So the fluvial transport term, of course, is going to be related to the water flow, and we often assume that's related somehow to some exponent. It's related to the local slope, so the steeper the slope, the more sediment transport we're going to get. And we often assume some sort of constant parameter which describes that relationship to slope. And then while the diffusive sediment transport term, we often assume, although not necessarily the case, we often assume that there's a linear relationship between slope and some diffusion coefficient or diffusivity. Right? And often these parameters, the M, the N and the D, have to be calibrated for a particular site. And so Greg's model, Siberia, is one of these models that incorporates all these processes to look at how landscapes evolve in the long term. Right, so the sediment transport equation predicts both erosion and deposition. So you move sediment from one place to the next, and if erosion at one place is less than the amount of sediment that's moved in, then you get net deposition. Whereas if the total erosion is greater than the total sediment coming in to that point, then you get net erosion. And that's how you get both. We often link these equations together on a finite element or finite difference grid. Right? So that's just a grid over which we simulate the points in our landscape. And we're able to dynamically adjust the topography in these landscape evolution models. Okay, so here's an example. Three-dimensional landform of a rock dump, junction dump, with its initial condition, right? So this was taken from some digital elevation model. We have the dump here, we have some steep slopes on the side of the dump here, and we've got 1,000 meters on this side and 1,400 meters on this side, right? Then we erode it for 1,000 years and see what happens. Okay, and we can do what if scenarios. So what if there was just bare soil? Well, we can make predictions about what the landscape would look like after 1,000 years with just bare soil. Okay, and this is for bare disturbed topsoil. Whereas if we had consolidated topsoil, maybe with a bit of vegetation on top, then this is what our landscape would look like. It would have eroded. Landscapes do erode, but nowhere near as much as in the case for the bare case, for example. So we knew that was going to happen before we had the landscape evolution model, right? We know that if a soil is more or less resistant, then we're going to get more or less erosion. But why do we use these models? Well, we want to better understand the long-term processes and these spatial interactions. So they can be very difficult things to predict. We can use them as management tools, so we can use what-if scenarios. Say, what if we did this? Would it be better in the long term? And we can also use it for design. So what if we design the landscape in this way? Would we have more or less stability in the long term? Okay. And we can make predictions about what the water quality and how much sediment is going to be mobilized into maybe sensitive areas that we care about. So we have to test our models. And so how do we independently test a model? Which is the best model to use? So there's 3 typical methods for testing a model. So you can compare them to natural landscapes. You can compare them to anthropogenic landscapes. And we can look at experimental model landscapes, right? So we can set up physically based model, this experimental model landscape, maybe with its own rainfall simulator, and have a look at what happens and how our model's making predictions about what's happening. So all these comparisons have advantages and disadvantages. So the advantages of comparing a model to a natural landscape is that we can design the model to represent actual field scale processes. The disadvantages are, however, that we don't know much about this heterogeneity in the landscape. We don't know much about the initial conditions for the model. Now, some people think that this is not important, and I would disagree with Greg in this case. My research is suggesting the initial conditions are important. We're not really sure about how climate and vegetation changed in the past, so we have to make some assumptions about what happened. And because of the long time scales involved, actually how we go about verifying our results, because we don't have the data, right? We're not going to be around long enough to measure what's happening in 1,000 years' time. The advantages of anthropogenic landscapes like mine sites when we develop these models are that we can actually observe field scale processes because they are often changing quite quickly. We have a site that's well characterized. Right? We know its initial conditions, we know when it was built, and we've often got data for what's been happening over the tens of years that the mine site's been around. Right? And the disadvantages are that the short-term processes may not be necessarily representative of those that are happening in the long term. So often we're seeing rapid development of armouring. We don't necessarily see soil development because we just haven't got the timescales. And vegetation and climate are often not changing too much, right, over the tens of years. But in the long term, vegetation and climate are all going to change. And then we have these physical models, these experimental landscape models, and the advantages of that are that we know the initial conditions, we can calculate the erodibility, and we can control the climate. Landscape evolution occurs quickly, and we can actually look at transient behaviours, right? We can look at what's happening to the landscape over, weeks rather than centuries that we can't observe at mine sites and other places. The disadvantages are how do we scale up? So how do we go from a small scale physical model to what's happening in the real world? We have to be careful about our boundary conditions. So are the sides of the physical model impacting what we observe within it? And are the processes that we're simulating actually the processes that are occurring in the field? Okay. So we have to be careful. So here's an example of a physical model, right? Greg set up a erodible material, which was actually some fly ash from a power station, and it was really fine-grained and highly erodible. We applied a little bit of water to it. It had a video camera which he could use to image the surface and generate three-dimensional data points for the surface. Then he had some sprinklers applying the rainfall, and he had cameras up here which were able to do the photogrammetry and get three-dimensional pictures. This was just an image what was actually happening during rainfall event. And these are resulting land. Okay, so Greg tested his models at this Tin Camp Creek site, which was up near the Ranger uranium mine, right, in the Northern Territory. It is a monsoonal climate in the tropics. It has 1,500 mils of annual rainfall, most of which falls between November to March. And it's also geologically complex and tectonically inactive. So that means there's no uplift. So the bedrock is not moving up or down or sideways. It's staying fairly uniform, at least over the time period that they're interested in. And the area is largely untouched by Europeans, although I dare say it, the native Australians had a reasonable impact in their time up there. So, methods of comparison between the landscapes. So there was some calibration of Siberia using measured sediments and hydrology. The field data was collected. Visual assessments of sites, slope area relationships were derived from DMs. There was hypsometric curves, cumulative area distributions, and width functions, and we'll describe what those are in a minute. But these are measures of the geomorphology of these landscapes. All right, so the calibration results using the model found that n was equal to 2.1, n was equal to 2, and this alpha parameter, which is related to that, is 0.42. Remember our slope area relationship? It was 0.42. And Greg also did some sensitivity analysis. So he varied these parameters plus or minus a little bit to look at their impact on the results. So, starting with an initial condition being the natural catchment, model the natural catchment elevations. So the natural catchment elevations divided by 100, right? So it sort of looks like much flatter relief. Then the elevations were uplifted to the maximum elevation of natural catchment. Then they just let the system evolve through time. So when you visually compare the Tin Camp Creek, this is the observed, with the model, Siberia, you can see that broadly speaking, there's a similar comparison, right? The landscape is evolving in a similar sort of way. Yeah. We have this feature through here, which is eroding. We have similar types of hills, although they're not as lumpy. Right? And again, comparing Tin Camp Creek with Siberia using different erosion parameters, you can see it's much smoother here in the Siberia model, right, than what's actually observed. When you turn the hill slope sediment transport right, turn off that diffusive sediment transport, then you get this very lumpy, etched by surface water flow landscape that's really spiky and has a high, high degree of microtopography. Whereas if you increase the diffusivity by a little bit more, then you get this much smoother sort of landscape that maybe is a little bit too diffuse. So the hill slope sediment transport parameter is somewhere between 0 and 0.1. So they can tweak that a little bit. But what you can do is you can actually compare other aspects, not just the visual comparison, but quantitatively you can compare the different sites and the different models. Right? So the open circles here are the catchments, and the models here is the other points here are the model with different parameters, different alpha parameters describing that erodibility, right? Erodibility factors. So it looks like the model's relatively insensitive to that parameter, because over a wide range of this parameter, you're getting similar slope area relationships, right? It's not quite picking up the finer resolution, but at the larger scale at least it's picking up the similar sorts of slopes. Although the parameters here with the points, the 0.57 seems to be doing a better job at the larger scales than some of the other ones. But again, you can vary that to double check. The hypsometric curve, right? It's a non-dimensional elevation. So they take the maximum elevation in the catchment and then divide by the and look at the cumulative area down the catchment, right? So non-dimensional area. So starting off at the top of the catchment, you have no contributing area to a point, and then right at the bottom of the catchment, or you have zero relative error, elevation, sorry, and all the landscape is potentially flowing through that point. So you have one here in the non-dimensional area. So the catchment has a curve that looks like this, and for a bunch of the parameters, it does an okay job, not a perfect job, but an okay job at reproducing the elevation area relationship for that catchment. There's also a cumulative area distribution that's sort of related to this. So we have the cumulative area in pixels on that axis, and the number of pixels on this axis. And again, a lot of the parameters look like they reproduce that pattern reasonably well, right, to the observed. And finally, we have what's called a width function. And the width function is really, you can think of it as we progressively move upstream from the outlet. So this is distance in pixels. This is distance upstream from the outlet. The width in pixels is actually the width of the contributing area. You can think of that. That's flowing to the outlet, right? So the width is the effectively the number of channels it intercepts, or the number of what we call, you can have a threshold here for the channels, but again, a lot of the model parameters are doing quite well, but some seem to be doing slightly better than others. So we can use a lot of these geomorphological descriptors of real landscapes and compare them to what the model's predicting. So here's a hypsometric function, right? Just reiterating, we have the maximum elevation here at the top of the catchment, and as we go down the catchment, our elevation falls. Water likes to flow downhill usually. And then at the bottom of the catchment, we have the lowest elevation. So we look at the cumulative area at certain elevations, and we can get a hypsometric relationship, right? It's the area of the catchment belonging to a class of the elevation contour. And there's a... So what we find for young catchments, we have a hypsometric curve that looks like this, right? And then as the catchment matures and reaches some sort of quasi-equilibrium, we end up in what's called this monadnock stage, right? Where it's essentially the height is concave as a function of the relative area, right? And so we can see that our catchment up here is probably in this mature equilibrium stage here, right? Somewhere in between the young stage and the fully eroded landscape, okay? It's heading off because it has a little bit of a toe down the bottom. So there's a hypsometric curve or cumulative distribution curve. Gives us information about the geomorphological characteristics of the catchment. The width function calculates a number of channels at successive distances away from the basin. Now, because this is the number of channels, you can define a threshold area above which you start to get channels developing. Now, the channels might be ephemeral, or they might be just little nicks in the landscape. But you can estimate that threshold area from field data, and then using your digital elevation model, estimate where channels begin. So then you can count the number of channels it crosses at a certain distance away from the basin outlet, right, as measured along the network. And the cumulative area distribution is calculated as the area of the catchment has drainage area greater than or equal to a specified drainage area. So it's like a cumulative probability function. Here's the probability that the area is less than some area A star, and these are the A stars. These are the drainage areas, right? So the probability that the area is greater than 10 square meters is almost equal to 1, because that's the pixel size. And then at the bottom of the catchment here, we have the probability that the area is greater than that will eventually go down to, 1 divided by the total number of pixels. And that's just comparing the community area distribution for the different models. All right, so these geomorphic descriptors are sensitive to the erosion parameters. But how sensitive are they to the initial surface conditions? So Greg created 100 catchments with random surface roughness, ran Siberia, and then he could place error bands around those geomorphic descriptors, right, to see what was the effect of the initial conditions, right? Slightly different random surface initial conditions. Look at how the model ended up, and again, Siberia looks like the real thing. So Greg suggests that initial conditions are not important, but when you have, I can say now from work that I've done, when you have strong eco-geomorphic feedbacks, potentially those initial conditions are important. So in a second part of his work, he assessed the reliability of the geomorphic descriptors, right? Using random elevations, Siberia simulations were not significantly different from the field catchment, right? And we can find circumstances in other systems where that's not necessarily the case. The initial conditions can be important. So he suggests you don't need to know the precise surface conditions to simulate the landscape, and that may not always be the case. So what effect does the catchment shape have on those geomorphic descriptors? So you can set up your model. For example, the real tin camp creep had a length to width ratio which is roughly 2.6 to 1, right? But you can set up models with a ratio of 1 to 1, a ratio of 2.6 to 1, or a ratio of 6 to 1. So what is the impact there? So here's an example, right? The real thing and the Siberia model with a ratio of 2.6 to 1 with chopped off sides and so on, okay? So you can see effects, and this ratio, even though the results are not shown, this aspect ratio is important to looking at some of those results. Right, I'm going to skip over that. So, how can we use these types of models in mine rehabilitation, right? So how can we assess erosion properties of different materials? How can we design hill slopes? Can we assess the potential for gullying and depth of gullying? And can we develop probabilistic assessments of erosion risk? So here's an example where you can use erosion models to predict gullying. It was an assessment that was looking at different cap designs for the sides of the rock dumps, and the model was able to quantify erosion incision, or the depth of gullying, and was also able to quantify the effects of different management strategies, right, on the landform evolution. And these studies were conducted on the ERA Ranger uranium mine. So here is an example of the initial topography that was simulated. So he simulated 1,000 years of unvegetated, unripped surface, right? So this is the results after the modelling. So there was considerable erosion in the central depression and on some of the batters down the side here, right? After 1,000 years, the maximum incision was 7.6 metres, and the maximum deposition in some areas of the model was 14.8 metres, right? So the elevation increased by 14.8 metres in some and decreased by 7.6 metres in others. Now, with vegetated and ripped surface, they assumed that changed the erosion parameters in some sort of systematic way. And what the model predicted was there was minor valley development in this central depression here. There was, on the edges and the batters here, there was only incision of up to 2.4 metres and maximum deposition of 4.8 metres, probably down in here. So if you've got a radioactive material buried 10 metres down, well, we know that after 1,000 years, it may not have been exposed. Cross fingers, touch wood. Okay, so here's an example of that. If the tailings containment implications, right? So let's say our tailings were buried below this dashed line, right? and they're radioactive and we have to worry about them in 1,000 years. The scenario 2 with the ripped and vegetated is shown in the top here, and the other scenario, unripped and unvegetated, is shown in the bottom one here. And we can see that in some places erosion was deep enough to get into those tailings and then start to mobilise some contaminants that we were worried about. Yeah. So this modelling was able to demonstrate approximate timeframes over which that tailings would be exposed, potentially where that it was most likely to be exposed, and so mitigation strategies could be put in place in those areas, and then more modelling done to simulate changes to that management to reduce the risk. Right? So, there's also probabilistic methods you can apply as well, right? So this is an example of probabilistic estimates of gully erosion risk assessment. You want to assess the high risk situations, right, using multiple simulations to develop some statistics of likelihood, right, using Monte Carlo analysis, and determine averages and also variation of ranges in some of the results of incision depth and where incision happened, the position on the hill slope, to provide a risk assessment. Right, so here's a scenario, slopes 1 to 5 to 100, not shown, and what's done is random soil properties distributed along these strips of hill slope, and then the hill slope's allowed to erode for certain periods of time. Right? And you can see that in this hill slope here, gullies started to develop and propagate upslope. And so what we were able to quantify from these simulations was the maximum depth of incision and where on the hill slopes these gullies were forming. Right? And so you're able to develop estimates of the average erosion rate with ranges between 76 and 91 tonnes per hectare per year, an average incision depth of 2.91 metres with some ranges, average positions of the maximum depth 50 metres along the slope, but they range between 34 to 63, and the average position of incision start, so where the incision exceeded some initial threshold, was at 10 metres. Right? So these sorts of things can help you guide where to throw on rock, for example, to mitigate some of these issues. So in conclusions, modelling. Landscape evolution models are very useful tools. Siberia and other models are undergoing continual evaluation, and erosion models provide effective landscape design tools for rehabilitation design.